Lattice energy is one of the important concepts to understand the ionic compounds. And we are learning now how to calculate that lattice energy. Truly, actually, three ways are there to find the lattice energy. The first that we are discussing in this part, that's a Born-Lande equation. It's a theoretical approach. Second, Kapuscinski equation. It is also theoretical approach. Without knowing the crystal type, we can find the lattice energy. And last, Born-Haber cycle. It is experimental way by which we can find the lattice energy. All those we need to discuss. Let us start with Born-Lande equation. Basic understanding about lattice energy, qualitative approach to compare lattice energy that we discussed in the last part. Now we should move to the quantitative finding or measurement or determination or calculation of lattice energy. It can be done by three means, three ways. The first, Born-Lande equation. Second, Kapuscinski equation. And third, Born-Haber cycle. First two are theoretical approaches and last one experimental approach. Let us discuss in this part Born-Lande equation. In 1918, Max Born and Alfred Lande proposed that lattice energy could be derived from electrostatic potential for attraction and repulsion. For that, they have suggested formula. This lattice energy includes attractive forces as well as repulsive forces. Before finding that actual formula, let me inform you the basic. That energy for attraction is equal to minus q1 q2 e square into m divided by 4 pi epsilon 0 r. Here m is a Madelung constant. We are discussing each term in detail later on. And repulsive potential energy ER equal to capital B upon R raised to N. That B is one constant they have considered. That's a repulsive interaction constant. And that N is a Born exponent. That Born exponent term will come where that N is coming exponentially. That question will be there. Therefore, I am showing this expression. Now, summation of those two, attractive energy, attractive potential energy and repulsive potential energy gives net potential energy. And that net potential energy, nothing but our lattice energy. And that lattice energy is equal to, means after simplification, minus NA into capital M into Q plus into Q minus E square divided by 4 pi epsilon 0 d in bracket 1 minus 1 upon n. Here Na means Avogadro number, M Madelung constant. It is related to structure of crystal. It is related to geometrical arrangement of the crystal. We have studied different types of crystal, especially cubic crystals. We have studied rock salt structure, cesium chloride structure, fluoride structure, anti-fluoride structure, perovskite structure. Yes, on the basis of the structure, this Madelung constant vary. I'll give more explanation about that. Wait. Q plus is a numerical value for positive charge. It's how much positive charge is there on cation. And Q minus is a numerical value for charge on anion. How much negative charge is there on anion? E square. Actually, it is a game of electron. Because of loss of electron, we get a charge positive. Because of gain of electron, we get a charge negative. And we generally say +1 charge and -1 charge, but it is due to charge of electron. Do you know what is the charge of electron? Yes, it is 1.6 into 10 raised to minus 19 coulomb. General way we say minus 1. But in true sense, the charge on electron is 1.6022 into 10 raised to minus 19 coulomb. We need to perform proper calculation. Therefore, whatever the positive charge is there, that is due to loss of those many electrons. Whatever negative charge is there due to gain of those many electrons. So multiplication of those will be E square. E square. Therefore, it is represented there. E square. And number we are considering in Q plus and Q minus. Small e is a elementary charge on the electron, that is 1.6 into 10 raised to minus 19 coulomb. Epsilon naught is a permittivity of free space, and 4 pi epsilon that we consider as a constant, and its value is 1.1 into 10 raised to minus 10 coulomb square per joule meter. D is the closest distance between ions, cation and anion, and small n is a Born exponent. Where is that exponential to anybody? But in our previous expressions, while considering repulsive energy, we have considered that power n raised to n, that n is a Born exponent. Typically, it is one number, its value is between 5 to 12. It is determined experimentally by means of compressibility factor, but here we are somewhat understanding it by means of electronic configuration, quantum number. It can be derived theoretically. See here, Madelung constant, how its value varies with change in the crystal lattice. Different crystal structures are represented and Madelung constant is written there. Sodium chloride means rock salt structure 1.75. Cesium chloride, it's a new type of structure. It is not only for cesium chloride, it is for the crystal lattices which show cesium chloride structure. That's a body centered cubic structure 1.76. For zinc blende spallary structure 1.64. Fluoride structure 2.52. Yes, as an example, I represented this. Now let us see how to find Born exponent. That Born exponent can be found by means of electronic configuration. If outer electron in cation or anion is in first shell, means like helium structure, value of N is 5. If it is in second shell, means neon electronic configuration, it is 7. If it is with argon electronic configuration, means it is in third shell, then 9 is a value of n. It may be in a 3p or maybe in 3d, outermost electron. Means in third shell, 9. If it is a fourth shell, means electronic configuration may be like krypton or Ag+, value of n is 10. If it is a fifth shell, means electronic configuration with xenon or Au+, value of n is 12. So from this, let us again understand that Born-Lande equation. Avogadro's 6.022 into 10 raised to 23. Madelung constant, just I said to you, depends upon crystal type, crystal structure. Q plus and Q minus charges we can find from the formula of the compound. E square means E, charge of the electron that we know. 4 pi epsilon 0 that we know, 1.1 into 10 raised to minus 10. And D, distance between the cation and anion, that we should know. Closest distance that we can find by means of summation of radius of cation and radius of anion. And Born exponent, value of n, it varies from 5 to 12. It depends upon electronic configuration of cation and anion. Yes. Now you will be the question, I said for only one electronic configuration. No, it is average value. Let us understand this by means of one example. Example is find lattice energy of sodium chloride using Born-Lande equation. Which data we need to find lattice energy? We need Madelung constant that will depend upon the crystal type. It's a rock salt type and its value is 1.75. We need Born exponent. For that electronic configuration we should know electronic configuration of Na plus. Where is outermost electron? Na plus means it is equivalent to neon. So Outermost electron is in second shell. So second shell means what is the value of the Born exponent? The value of Born exponent is 7. Other ion is chloride. Chloride means 18 electrons. 18 electron means it's orgone electronic configuration. So it is in third shell. Outermost electron is in third shell. So what is the value of Born exponent? It is 9. So average of 7 and 9, that is 8. That will be the Born exponent. What is the value of D? Distance between the cation and anion. For that we need values of sizes. Radius of sodium ion and radius of chloride ion. They are simple summation. Just substitute the value. Purposely I am representing here the values with their units. So that cancelling of any unit occurs, you will understand. The first term is Avogadro's number. Unit is per mole. No other entity is there which can cancel or multiple the unit, so unit will remain as it is. Means in the final unit of lattice energy, per mole term should be there. Then Madelung constant, it has no unit. Afterwards, product of charges. Yes, charge we are measuring in terms of coulomb. Two charges, their multiplication. So coulomb square is represented right side in the numerator. In denominator, unit for 4 pi epsilon 0 is coulomb square per joule per meter. Here, coulomb square and upper coulomb square will get cancelled. Now per joule and per meter will be there. Afterwards, distance between the cation and anion, that is in terms of meter, 283 into 10 is to minus 12. Why minus 12? Because the distance was in terms of picometer. Pico means 10 raised to minus 12. It is very important representation of unit in SI pattern. Now this meter in the denominator and per meter, they will get cancelled. Now what is not cancelled from the denominator? Per joule. As it goes to the numerator, it will become joule. So final unit will be joule per mole. And for value of Born exponent, there is no unit. Now you can simplify that. If you want to simplify, simplify the bracket first. 1 minus 1 upon 8 means what? 7 upon 8. And do multiplication and the division, you will get answer and sign will be negative. Why? Because we are talking about formation lattice energy. If it would have been the dissociation lattice energy, lattice breaking energy, then it will be the positive. Yes, see the answer now. Answer after calculation is minus 758 kilojoule per mole. The term kilo came because of the expression into 10 raised to 3. It is a proper way of presentation. Therefore, I represented. If you see the formula, in that kilo term was not there. That is just the conversion. I hope you will understand the decimal point conversion, power conversion. Experimentally, when we determined the lattice energy, the answer was 787 kilojoule per mole. Values are very near, hardly difference of 30 kilojoule per mole. I need to find percentage difference. How to find that? Take a difference of these two, divide by expected value, means experimental value, that's a 787 kilojoule per mole into 100. You will get answer 3.7 percentage, means it is less than 5%. What are the differences are coming? Less than 5%. Without doing experimentation with a theoretical calculation, we could find that lattice energy to this accuracy. That's the importance of Born-Lande equation. Let us further understand the application of Born-Lande equation for calcium chloride lattice. Formula is in front of you. What we need for that? Madelung constant. And calcium chloride has fluoride kind of structure, CaF2 structure. And for that, Madelung constant capital M is 2.52. We need to find Born exponent. For that, we should find individual values of n and then average value. electronic configuration of calcium plus 2. Calcium atomic number 12. By removal of 2 electron, now 10 electrons will be there. Means electronic configuration of neon. Final last electron is in second shell. So for second shell, value of Born exponent is 7. What about chlorine? Chlorine atomic number 17. By taking 1 electron, 18 electrons are there. Yes, it is electronic configuration of argon. Third shell. So Born exponent value is 9. Average value n is equal to 8. What about the value of D? It is the internuclear distance between cation and anion. Radius of cation, radius of calcium plus 2 is 114 picometer and for chloride is 167 picometer. Summation of them 281 picometer. Just let us substitute these values in that formula. Have a look on represented units and final unit will be joule per mole. But after conversion, after considering power to the 10, answer will be kilojoule per mole. Just Avogadro's number 6.022 into 10 raised to 23, Madelung constant that I said 2.52, charge on calcium, yes 2, charge on chloride 1, and charge on electron, because whatever the plus 1 minus 1 charge we consider in terms of electron. So Coulombic charge of the electron 1.6 into 10 raised to minus 19 and its square. It is very important. Value of 4 pi epsilon 0 is 1.1 into 10 raised to minus 10. And what about D? That we did calculation. That is a 281 picometer. Means 281 into 10 raised to minus 12 meter. And the term in bracket simple 1 minus 1 upon 8 means it's a 7 upon 8. Do the calculation. You will get answer for lattice energy as minus 2199 kilojoule per mole. And experimental value for it was found to be 2255 kilojoule per mole, hardly difference of 56 kilojoule per mole. If you find percentage, means this difference divided by experimental value means actual value we are considering into 100. The answer will be 2.5%, means it also is less than 5%. Error is less than 5%. Difference is less than 5%. That's the importance of Born-Lande equation. Yes, student, let me know whether you understood this concept or not. Prove by solving this problem. You have to find lattice energy for cesium chloride using Born-Lande equation. And after finding lattice energy, you have to find percentage difference with experimental value. I had given experimental value. See which things I have provided for you. Madelung constant, cesium chloride, body center cubic structure, 1.76. Radius of cesium plus, 181 picometer. Radius of Cl minus, 167 picometer. Summation, that will give you value of D. But that will be in picometer. You have to convert it to meter. How? Into 10 raised to minus 12. That's the meaning of pico. Born exponent that you have to find. Get the electronic configuration of cesium plus. See outermost electron is present in which orbital. Means it attains configuration of xenon or krypton. That you find out. And what is the shell number? Accordingly, you will get the value of n for cesium plus, value of n for Cl minus. Take average value that you have to substitute in that formula. Avogadro's number 6.022 into 10 raised to 23 per mole, 4 pi epsilon 0, 1.1 into 10 raised to minus 10. Those values are known for you. Just do the calculation and I want answer in comment box, answer for lattice energy. After finding that answer, you have to find percentage difference among lattice energy with experimental value. What is the experimental value? Minus 661 kilojoule per mole. How will you find that? Your calculated value minus this value divided by experimental value, which we are considering as a true value, into 100. That will give you the percentage difference. So percentage difference also you have to mention in the comment box. Let me see how many of you answer promptly. I'm waiting for your answers. Yes, Born-Lande equation can give us good lattice value. Difference range is only 5% compared to experimental value. But in the days 1918, means by second decade of last century. Considerable good idea Born and Lande has given. Let us see how to find lattice energy if we don't know the lattice structure. Because if we don't know lattice structure, we cannot find the Madelung constant. So some approximation is done by Kapuscinski. Let us see what is the Kapuscinski equation and its application in next part.